Welcome back to the lecture series on image recognition with neural networks. This is lecture 4. What is a derivative, a gradient? The objective for this lecture is we'll talk about what is a slope of a line, then we generalize that into a derivative, and then we generalize that into a gradient, and then we'll talk about how to interpret the gradient. The interpretation of the gradient is actually very simple, and is actually going to be the main ingredient for an algorithm called gradient descent, which we talked about in the last lecture. This is really the last algorithm that we need for our program. So if you've never taken calculus before, here's your chance to learn calculus and multivariable calculus in about 20 minutes. And I promise that there's going to be a lot of picture, a lot of intuition. And the focus here is on understand the intuition behind it so that we can understand the algorithm. And so it's going to be a good lesson. So intuitively, the slope of a line measures the steepness of a line. It measures the rate of change of the output y with respect to the input x. So for example, here's an equation of a line. The slope of this line is 3/2. What that means is that if x increases by 2, then y increases by 3. So it tells you how fast y is changing in terms of x. So here's an ant analogy that we use repeatedly throughout this lecture. Suppose you have an ant that is on a line of slope m. The slope is a measure of how difficult for the ant to walk up the line. So for example, here are two lines. You have two ants. One of them is on this green line. The other one's on this blue line. The slope of this line is 2, rise or run, right? Rise over run. And the slope of this line is 1/2. And so this says that it's harder for this ant to go up this line than for this ant to go up this line, because the steepness of this line as measured by the slope is bigger than the steepness of the blue line as measured by its slope. The derivative is a way to generalize the slope of a line. In fact, the derivative of a curve is a measure of the steepness or the slope of the curve, and we'll denote the derivative function by f prime of x, or sometimes df dx. So let's look at this picture of this. If you have a function that has a derivative, then it is called differential at that point. But we don't really need that, really. Okay, so here's the ant analogy again. Suppose you have an ant that is trying to climb up this curve. And of course, because this is a curve, it's easy to see that the ant's experience in climbing up this curve is different at every point on the curve. So for example, if the ant is at position A, then you can see that it's actually harder for the ant to move up the curve than it is once it gets to position B. In fact, the closer it is to the top of the hill, the easier it is to climb up the hill. And so it's easy to see that the slope or the derivative at A should be bigger than the derivative at B. In fact, the derivative at C should be 0. So again, the derivative is just a measure of the steepness of the curve, in the same way that the slope of a line measures the steepness of the line. So it's very simple, the derivative. Another way to think about the derivative is that we can look at the slope of a line called the tangent line. So the derivative is the slope of the tangent line of a graph. The tangent line can be thought of as the line of sight. So here's the ant again, is at position A, and imagine that the ant is looking, right, as he's walking up this hill. So the ant's line of sight, the answer right here, the ant's line of sight is the tangent line. Or you can imagine if you're on a roller coaster or something, this is the roller coaster, then your line of sight, the way that you're facing, is the tangent line. Or you can imagine if this is like Cyclops, if he opens his glasses, then the ray that comes out of Cyclops' eyes from X-Men is the tangent line. That's another way of thinking about that. And so the derivative of the function at A is the slope of this tangent line. So in this case, you notice that the slope of this tangent line is rise is 4, run is 1, so the slope is 4. Therefore, the derivative at a is also 4. So we say that f prime, which is the derivative function, at -1 is the x value of the point a, f prime of -1 therefore is 4. So again, that's a very intuitive definition. Now, if we zoom into the point A repeatedly, we notice that the function flattens out and looks more and more like the tangent line. The more you zoom in, the more the function becomes more and more like the tangent line. In fact, if the ant is small, it does not see the curvature of the function. It thinks that it lives on the line of slope 4. So we think that, the ant's being kind of silly, that how could it not see the curve? Well, in fact, it turns out that we have made this same mistake. We at one point thought that the curvature of the Earth is flat, and we thought that the Earth was flat because we don't see the curvature of the Earth because the Earth is so big. So it's a similar analogy. So here's a quick recap. So as the ant is moving up this hill, at every point on the curve, there's a tangent line, the line of sight. The slope of that line is the derivative. So for example, f prime -1 is 4 because the slope of the tangent line is 4. At b, if I look at this line, the slope is actually rise is 2 over 1. So f prime at 0 is 2. And finally, when you add point c, which is when x is 1, the slope here is 0. Therefore, f prime of 1 is 0. That's it. That's calculus 1. Given a function f of x, we're going to denote f prime of x to be the derivative function. So this is a function, and this is the derivative function. It tells you the slope of the tangent line. So as an example, the f of x is the purple graph, and then the black graph is f prime of x, its derivative. So let's look at an example. Look at the point A. Notice that at the point A, the tangent line has slope -1. So therefore, f prime at this point should also be -1. And in fact, it is. If we look at f prime at 0, we see that it is -1. So again, here, the function is the purple curve. The point on f prime tells you the slope of the tangent line on the purple curve. So f prime evaluated at 0 is also -1, so f prime of 0 is -1. As another example, if you look at this point right here, the slope here looks like to be 0, and you look at f prime at that point, you see that it's also 0. So f prime at here is also 0, and similarly in this point, the slope here is 0, so f prime at that point is also 0. So the black function tells you the slope of the tangent line of the points on the purple graph. If you've done calculus before, you might remember some of these rules from calculus, but if you haven't, then that's fine. But I just want to quickly run through this real quick. So the derivative of a constant function is 0 because it's a horizontal line everywhere, so the slope is 0. The derivative of a line should be m. The derivative of a line should be the same as the slope of the line. So the slope of the line is m. This is called the power rule. If you want to find the derivative of x to the n, you bring down the n and you subtract 1 from the power. If you do want to differentiate a function with a constant, the constant can be moved out, and you can leave the constant alone. So when you differentiate a function with a constant, that constant stays there. To differentiate a sum of function, you differentiate them separately, then we add them. To find the derivative of the difference of two functions, we find the derivative of each of the individual functions, and then subtract them. So these are just basic rules that from calculus. Again, if you don't understand those, you don't need it to understand the algorithm. So here's just a quick example for those who have done some calculus, and this is kind of easy to do. So here's a function x cubed minus x. If I want to find the derivative or to differentiate this function, I differentiate them separately and then I subtract them. So if I were to differentiate x cubed, the power rule says you bring down the 3, you subtract 1. To differentiate x, again, this is a line, so the derivative of this should be the slope, which is -1. Here's another example. If you want to pause the video and work through this, this is just basically differentiating each of these functions using the power rule, as we saw earlier, and then add or subtract them. So it's just go over that. And again, if you haven't taken calculus, and this is not necessary for writing the program. Let's talk about partial derivatives. Now this is calculus 3. If you take a multivariable calculus in college, this is what we talk about here. Okay, so suppose you have a function of several variables. So you have many variables. So this is a vector, and the output is one variable. So this is a real value function. The partial derivative of a function f that is many variables with respect to a particular variable is denoted by df dx. Again, this is the partial of f with respect to xi. Sometimes we just denote this whole derivative simply as df dxi. So this is the derivative of f with respect to one of the variables. So the partial derivative is simply the derivative of f with respect to xi, treating the remaining variables, the one that's not xi, as constants. So that's the key to understand this, is that when you differentiate partially, then what you're doing is you're just treating every other variable as if they're constants. So what that means is that this is essentially calculus 1 again. So this is really the same derivative that we just learned just now. So let's see some. So computationally, the partial derivative is exactly the same as the derivative of a single variable from calculus 1, since we're keeping the other constants, the other variable as if they were constants. So if f is a single variable input, then the partial of f with respect to x is the same thing as df dx. So they're the same. So again, the partial is a way to generalize the derivative. So let's do an example. Here's a function of two variables, and we want to find the partial of f with respect to x and the partial of f with respect to y. And so to find df dx, or the partial of f with x, we're treating y as if it's a constant. So that means 3 is a constant, and so is y. So this is actually very easy. This is just calculus 1 again. So let's see it. So again, 3 is a constant, y is a constant. So again, if you have a constant, you can pull it outside of the derivative. It just stays there. And then we just differentiate x squared. X squared is just the power rule. X squared is 2x. And so the answer is 6xy. So this is, even though it's really part of calculus 3, the computation is still the same as calculus 1. In fact, the interpretation, as we see in a second, is the same interpretation. In the same way, if you want to do the partial of f with respect to y, we're treating 3x squared as if they were constants because we're only changing y. And so that's a constant, we keep it alone. And then to differentiate f with y, it's just simply 1. So there's how you do partial derivatives. And then again, here's an example. You're welcome to kind of try this out. Again, you should differentiate these separately, treating y as a constant in all cases. So for example, if this is if y is a constant and this is 0, and everything else is just as before. So so feel free to kind of look over this example. If you've done calculus before, then you should be able to do this. If you haven't, again, this is not necessary. I just want to give you some examples. Okay, let's understand the intuition behind the partial derivative. Again, all we need is just understand the intuition so we know how the algorithm works. We don't have to worry too much about the computation. Okay, so here's a function, fxy, which is a surface. The surface of this is called a parabola. And so it looks like this. So again, the domain here is xy, which is the gray plane. And then the output is a number, which is the height. So here's, for example, the xy is 2, 3. So again, this is, I believe, yeah. So this is x and this is y. So if x is 2, 3, then f of that, if you plug it in, you get 1. So for example, here's 2, 3 on the floor, on the gray plane. And then the function gives you the value 1, so that's the height. So this is the graph of all the height of the function. So 2, 3, and then the function output is 1, therefore this point is 2, 3, 1. Okay, so again, let's just calculate the partial derivative. Again, we can check that this is the partial. If I plug in the point 2, 3, we get negative 2/3. So let's see, what does that mean that the partial of f with respect to y at 2, 3 is negative 2/3? Well, it's the same interpretation as the single variable derivative. So here's the So by definition, the partial of f with respect to y means that you find the derivative of f, again, the slope of the tangent line, with respect to y by keeping x constant. We're keeping x constant at the value 2. So let's look at a picture of this. So on the graph of fxy, if we're treating x as a constant, then it means x is always 2. If x is 2, I can plug it into the function, plug it 2 into this point, this x right here, and I get this function, which is now only a function of y. Remember, we're keeping x constant, y is the only thing that's changing, so this is a function of one variable, a function of y. And so the graph of this, if this is a function of one variable, then this is a parabola. Y squared is a parabola in pre-calculus. And so let's look at this curve again. So the turquoise plane right here is the plane given by the formula x is 2. So in other words, if I move on, every point on the turquoise plane has the property that x is always 2. And so if the ant is at this point on the point A, and is only allowed to move in the y direction, meaning that x has to be constant at 2, then that means that the ant can only move in the direction given by this plane. In other words, the ant is only moving on this curve, which is exactly the parabola given by this function, keeping x constant at 2. And so this is the parabola, is the intersection of the turquoise plane with the graph. And so the intersection of this plane with this graph is this parabola. And so the way we interpret this partial derivative is exactly the slope of this curve, which is, again, calculus 1. So the parabola is the intersection of the plane and the curve. And so that means that, so for example, in this case, that means that the tangent line to this curve, again, one single variable curve, the tangent line of that curve is negative 2/3. So if I were to use the ant analogy again, if the ant is on this surface and is only walking in the direction in which x is constant, x is 2, then it's walking parallel to the YZ plane. Again, look at this. This is the Y axis, the green axis. This is the X axis. This is the Z axis. So if I were to walk along the direction of the turquoise plane, then it's actually walking parallel to the YZ plane. So make sure you understand that. And if it's walking in the direction of increasing y, because we're going to have to be going to the right, in the direction of increasing y, then this says that the slope that the ant is experiencing is negative 2/3. So the slope of this curve is negative 2/3. That means that the ant is going downhill, and the steepness of that downhill is 2/3. So the interpretation for partial derivative is exactly the same thing as for single variable derivative. So if x is fixed at 2 and y is allowed to change, then it traces out this green curve. Right? So again, if the ant is moving on the green curve, that means it's going only in the direction of y, keeping x constant at 2. And that means that the tangent line of the green curve is, again, we saw earlier, negative 2/3. On the other hand, if we're fixing y at 3, so now we're fixing y at 3 and we're changing x, then that means the ant is moving on the blue curve. And the slope of the tangent line at that point is given by the blue line. And the slope, you can check easily that the slope of that line is, again, differentiate with respect to x, plug in 2, 3, and you get negative 1. That means that is, if it's going in the positive direction, here's the positive direction, then it's experiencing a negative slope of 1. The slope is negative 1. So that's it. That's how we interpret partial of f with y, partial of f with x. It's the same interpretation, which is the slope of a tangent line of some curve. Okay, now let's put it together and come up with something called the gradient. So again, you have a function of multivariable, many variables, n variables in this case, and the function has to be real value. This has to be a real value function. The gradient of f, by definition, is an n-dimensional vector. It's a vector, and it's found by taking the partial of f with respect to each of the variables, and then just put it together into a vector. So we use the del notation here to denote the gradient of f. So for example, if f is a function of 2 variables, then the gradient of f is differentiate f with respect to x, differentiate f with respect to y, and so we can check that these are what you have. So this is the gradient of f at xy. To find the gradient of f at a certain point, say 1, 2, you plug in that point 1, 2, and you get this vector. So again, the gradient of a function at any given point is a vector at that point, and this is the vector given by the gradient. So we want to interpret this vector in a second. So intuitively, what is a gradient? It is a way to generalize the derivative. The gradient is a vector, so it has two things. It has a magnitude and a direction. So we want to focus on really the direction. The direction is what we're going to need to use for our algorithm. So again, here's the ant again. The ant is on this curve. And so here's how you interpret the gradient. The ant can move in any direction it wants. It can choose to move only along the x direction, as we saw earlier with the partial derivative, or it can choose to move along the y direction, which is given by the green and the blue lines. Or in fact, it can choose to move in any direction. Say, just have to move in a random direction, given by the orange curve. So the ant is free to move in any direction. So the question here is that which direction will allow the ant to get to the top the fastest? Suppose it wants to get to the top of this hill as quickly as possible. What direction should it go? So amazingly, it turns out that the direction given by the gradient is the direction that will get the ant to go up to the top of the hill the quickest. And then, so that's the direction given the gradient. The magnitude of the gradient turns out to be a measure of the steepness of going in that gradient direction. So the ant wants to go in the gradient direction, then it's going to go to the top of the hill the fastest. And the magnitude of that vector, of the gradient vector, tells you the steepness of going in that direction. This is a beautiful geometric interpretation of the gradient. And it's actually a very useful one. So as a quick example of why this is useful, if you were writing a game, writing a physics engine or something, and the game is a game of golf, and suppose a player hit the golf ball and the ball bounces around, eventually landing on some hill, and once it stops, the ball has to roll in some direction. Well, which direction should it roll? Well, it's going to roll, well, not in the gradient direction because that's going uphill. The ball is going to roll in the direction opposite of the gradient, which is the direction of the biggest descent. So the ball is going to roll in that gradient direction. So that's how you can simulate physics and make ball rolling more realistic, is to let it roll in the direction of steepest descent, which is given by the gradient, which is easy to compute. Okay, so just one more picture for this. So same function as before. Here's that point A. And again, the point A is actually on the domain of the function. 2, 3 is the input. So D is this point on the floor, which is the domain of the function. So notice this D is at the point 2, 3. And so if I look at the point D, I notice that, again, this is a two-dimensional vector, D. And if we look in the direction given by the gradient, which is -1, -2/3, so here's D, the direction of -1, -2/3 is this direction. So that means that if the ant will walk in this direction, then that means it's going to go along the orange curve. Again, going in the direction of the gradient will help it go to the top of the hill the fastest. So that's how you want to think about the orange curve. Again, the gradient is it's not a three-dimensional vector. It's a two-dimensional vector in the domain space. It tells you the direction that you should be facing if you want to go up the hill the fastest. So the gradient direction is the direction of largest ascent, going up the hill the fastest. The negative gradient direction, which is the opposite direction, you just negate this vector and get the negative direction. Then it's the direction of largest descent. So this fact is central to the gradient descent algorithm, which is the main algorithm that allows us to write a program that can recognize images. And it's just a beautiful result here. So here's a final picture here. Again, if I were to go in this direction, that's the direction of the biggest increase. The magnitude of the vector, so in this example, if I find the magnitude of the vector, which is the Pythagorean theorem, then that would give me 1.2, and that 1.2 is the slope of this tangent line. This is a beautiful result. Again, if you take multivariable calculus in college, you will have seen this result. Okay, so one more clarification on notation here. So sometimes when we write notation, if a function is a vector, if a function take a vector input, let's say the vector input is given by x, the vector x, then the gradient of f, just like we saw earlier, is the del of f, which is the partial of f with respect to all the variables, x1 to xn. And the notation that we use is to say df dx, where x is the vector form. So this is another notation for this vector. So this is the gradient notation. Now, if a function is a function on matrices, so if you have a function that takes matrices, as we saw in lecture 2, and output a real number, W is an m by n matrix, then the gradient of f is an m by n matrix. So it has the same interpretation. It's still the direction of largest increase, and this is now a matrix. It's no longer a vector, it's a matrix. And so the notation for this is that we'll say df dw, again w is an m by n matrix, so this derivative is a matrix derivative, and it's simply, again, look at all the entries, all these w1, 1, w1, 2, those are real numbers. So this is, again, single variable calculus. In fact, I should write df d, this is fine. Yeah, so this is single variable calculus. This is the partial of f with respect to w11, keeping the rest of the w constants. So these are the partial of f with respect to each of the individual elements of the matrix w. And again, this big matrix is the gradient of f. In other words, it's still, the interpretation is still the same. Is you're going to represent the direction that I move in the w direction that will help me increase f the fastest. So this matrix points in the direction of largest increase for f. So this is what we're going to use because, as we remember, our function is of functions on matrices. Okay, if any of those material was confusing, all you need is just an intuition for the gradient, which is simply this. Given a function f, the gradient is a vector that points in the direction of biggest increase, and the opposite direction, the negative of the gradient, is the direction of largest decrease. If you understand that, then the algorithm is going to make sense. Okay, that's it. We've covered calculus 1 all the way to calculus 3. We understand what the gradient is now, and now we can finally understand the gradient algorithm, which will allow us to find the best parameters, W and B, that minimize the cost, and therefore maximizing our model, and then we can recognize images. So in this lecture, this is mostly math prerequisite, so there's no homework for this one.